Good afternoon. I'm Pedro Mestre from CEiiA, Center of Engineering and Product Development in Matosinhos, Portugal. And I'm going to present to you a work called A Platform Architecture for mHealth Internet of Things Applications. Well, in the last few years, there's been a focus in very specific applications of IoT or Internet of Things. And one of those target areas has been the Internet, or better, the Health Internet of Things, mHealth IoT. As any other form of IoT, not particular to mHealth IoT, there is a phase that is a challenge for developers and integrators, which is the integration challenge. And why is this a challenging phase? This is a challenging phase because we are trying to put together devices, protocols, applications that were developed by different teams, by different companies, by different developers. We have, in fact, very different formats. For example, XML, JSON, CBOR. We have different communication protocols. We have CoAP, we have MQTT, we have Blackwing that Sérgio showed before. And this can be standard, but there are different standards, and they don't fit together, or they don't link without anything, without having something here in the middle that will provide that link. Also, there is another problem that we might have in integration, which is integration might lead to some solution, some piece of head of code that will fit very well that particular solution, that particular problem we are trying to solve, but will not solve all the problems that are similar to that one. That's what we want to, let's say, fix with this project, with this work we're presenting here. We want to reach a IoT platform that can cut down the integration time by getting some components that are standard components, or that can communicate in the standard way, or in a very well-defined way. We want to reach a IoT platform can be used as for generic IoT applications, of course, that can be used for mHealth applications, and with a seamless integration of all components. What we want is that components can be anytime added or removed from the platform. This means that it's dynamic. We can add, remove without hard coding anything in the code of our application. We don't want this at compile time, or we don't want this at startup time. We want this at any time. This means that components can be added or removed at runtime. No need to shut down the platform without any downtime. Just have everything working. Of course, without having negative impact on the running platform or any component that is working there. In here, we have a diagram where we have generic architecture of mHealth IoT platform. We have from the hardware to the application, passing through the glue that puts these two layers together, or the mHealth IoT platforms. We have data from sensors that monitor patients, that monitor ventilators, that monitor whatever we can monitor in a hospital system, but not only devices that do this, also patient records. We need to be able to send this information to the applications for the billing software, for the emergency vehicle tracking, to send messages, to track patients, and so on. For that to happen, we need in the middle a layer that will be able to process information, to secure this information, to provide the correct APIs for us to access the information and for the information to reach the platform. The correct software and hardware for these platforms to run. We can put this in a cloud platform, or we can just get the bare metal and do our own cloud platform. Okay, well, this is the part that we did. We did in our case, we got the bare metal, install all the software we need, and we are testing also our own private cloud. In our case, we are using a Kubernetes API, which is suitable for managing our software pods, and whenever a pod is in trouble, it crashes, it restarts, and we can use it also to have more computational power or decrease the needed power for our applications in a more or less dynamic way. Nevertheless, we need something to run on this. And what are we running on top of our cloud platform, our cloud system? Well, we are running something that is based on this diagram I have in here. Well, the story starts on the left with devices, and devices need to send information to somewhere. Devices use protocols. They use from level 1 protocols to upper layer protocols. They have different physical layer ways of sending information. Probably most of them will be using wireless communication systems, but with different codings. Different protocols can have Wi-Fi, NB-IoT, we can have BLE, whatever. Even in the upper layers, we can have different things. We can have devices that are IP-based. Those are not IP-based. For each one of these, we need a set of support hardware and support software for it to be able to communicate. And for this low-level support, we have what we call in our architecture an ecosystem. This device ecosystem handles whatever the needs of these particular devices. And then we'll have a layer, a driver, that is able to send information forward. For this information to go forward, we specify a set of interfaces, and these interfaces are the same whatever the type of device that we have, whatever the protocol they use. So this is the part where we start to forget what type of device we have, and we start to have a generic IoT device. If I want to add support for a new type of device, a new type of protocol, I just add a new type of ecosystem. These ecosystems, or the idea of this ecosystem, is for them to be reusable, to be made in a way that they can be reusable, and whenever we have a new device or a new set of devices that use a protocol that has already ecosystem implemented, just reuse it. Information will reach the mediator, and this mediator will look at the information and decide what to do with it. What is going to do? Display in a dashboard, send to an APP, store in a database? Well, the mediator doesn't know it beforehand. The mediator, when it starts up, might not know. It doesn't know for sure when it's compiled and started the first time. There is nothing hard-coded here in the mediator. Of course, this mediator, if it shutdowns and comes up, it needs to remember what it was doing before. So it needs to have some basic configuration, startup configuration. But nevertheless, at runtime, we can add new rules, remove rules. We can at runtime say that this device here, D1, sends information to this dashboard, and this D1 also sends information to this database. And this A1 only sends to the APP, nothing else. This is made dynamically. This is made at runtime. This configuration is not hard-coded anywhere. Any device can send information to any data consumer. Okay, the devices don't know where the information are going, the mediator knows, and the mediator is the one that knows the consumers. To be able to send to any consumer, the mediator doesn't care what type of consumer they are. What the mediator sees is a data interface, a standard interface of what a consumer needs to have. What are the actions of a consumer? The same way, the mediator also accepts requests for the devices. Either it be a command to change the state of a device, or to do an actuation, to change the configuration, a reboot, an update. Okay, whatever we want to do, there's also an interface that specifies how can I do it. Once again, the link between devices and the application that controls it, devices and where the data is stored, is not there at runtime. The same way that with ecosystems we can reuse them, the idea of consumers and common providers, the idea is the same. You do for one technology and then it's reusable. For example, in our case, I can tell you we have here already ecosystems for Blackwing and Co-op, and we have in here interface for MQTT that consumes information and sends comments back. We have here REST APIs to send information to outside or for consumers to come and get that information. To manage this mediator, it's not different. We also have an interface that says which functions are available in the mediator, and for now we have a CLI information application that manages the mediator and a web application that is easier to use. And by providing these interfaces, by providing this mediator, we can connect any device to any application at runtime without nothing hard-coded. And to test this, we set up a platform that has a device ecosystem that receives data from devices that use Co-op, a device ecosystem that receives data from devices using Blackwing, one mediator, and one data consumer that sends information using a WebSocket to a web application, this one here. And to test this, we just flooded the system with as many messages as possible that we could send, and we did a first test where we were sending information between the ecosystem, not the device, the ecosystem and the mediator. And in this test, we were able to reach around 1 million messages a minute. The next test was using a device sending message to the ecosystem, and from the ecosystem sending to the mediator. What we're doing with this message, nothing, we're just dropping the message. But before dropping the messages, we are looking at them, analyzing them, and see if they are valid or not. They only don't go after the mediator, they are just dropped. We are here trying to see what is the ability of mediator to receive messages and process them. And in here, we went from 1 million to 380,000 messages a minute. One very important point. We only have one replica of the mediator. We didn't do any tests with multiple servers attending the client. And then we did a last test where we do the full cycle, and information comes from device, is processed by the mediator, and is sent to a consumer. which the consumer that then shares information in a web page and displays in a web page the real-time placement, in this case, of emergency vehicles. And in this case, we had around 285,000 messages a minute. Okay, we reached here with this project a platform that is able to do the seamless integration of devices. To help this seamless integration based on the REST and gRPC APIs, we developed a framework that can be used by clients to generate ecosystems, consumers, and common producers. This means that whoever wants to build applications for this platform will be able to use this framework and without concerning how the communications are made, how those interfaces are specified. This framework has been developed in Python and Java. We have both versions and is currently under development and is being tested by a third party, someone outside CEiiA, and it did not participate directly in the building of this system. They are testing it and they are integrating this in their applications. This partner already had their own independent IoT platform and now are doing integration of their components with our platform. Of course that the scope of an application of this platform is not limited to what I presented here. It can be applied to any IoT application. In fact, we are testing this in applications related to mobility. Related to future work, we are planning to add new functional components. One of them is the translator that is able to translate information between data formats. Now it is embedded in other components. We want it to be outside for better code reusability. And we also are handling the issues related to security and data protection. We are using gRPC for communication between components. It can be used over HTTPS, so we ensure that encryption. And for now, this platform as it is, it doesn't store data. So we here don't have, in this part of the platform, we don't have concerns related to data protection. Well, this is the funding of this project, and thank you for your attention. I don't know if you have any question, I will answer.